Okay, so I've put together a little review for the exam next week on chapters 1 through 3. I am not going to spend time going through all the terms and words that you see on this page. I'm going to focus on the more difficult stuff, but I did make this list because these are things that you need to know, whether they be definitions or characteristics. So you can pause the video and you can write them down, or you can take a screenshot of them. But those were the top ideas that I came up with. So I'm going to begin by reviewing the rules of significant figures. Remember that non-zero digits are always significant. Any zeros between two significant digits are significant. So for example, if I have 12.2, those are all non-zero digits, so they're all significant, so that would be 3 significant figures. If I have 105, that is a zero between two integers, so they are all significant, so that's also 3 significant figures. However, if I have 1050, that trailing zero does not count because there is no decimal. So this would still be 3 significant figures. However, if I add the decimal there, then that zero becomes significant, and that would be 4 significant figures. So the big thing is trailing zeros only count when there is a decimal. Leading zeros never count. So if I have 0.0023, only the 2 and the 3 are significant. So that's 2 significant figures. However, if I have 0.00230, the trailing zero in this case is significant because I do have a decimal present. So this would be 3 significant figures. So to summarize, leading zeros are never significant. Trailing zeros are only significant when there is a decimal present. Integers are always significant, and zeros between two non-zero digits are always significant. The most important thing to remember about addition and subtraction, multiplication and division is you're always going to do the math first. Once you have the math and never round until the very end, then you apply the rule. So here I have an example of 3 problems. 32.01 minus 1.2, and the first thing I do is the math, 30.81. Now I'm going to look at the least number of decimal places. 32.01 has 2 decimal places, 1.2 has 1 decimal place, so my answer can only be to 1 decimal place. I'm going to look to the right. I'm less than 5, so I'm going to round down. So my answer is simply going to be 30.8. On the next one, 16.1 plus 2.43. 16.1 has 1 decimal, 2.43 has 2. I do the math, I get 18.53. My answer can only have 1 decimal. So that's the 5. I look to the right. It's less than 5. I round down. So my answer is 18.5. And on my last one, 15 plus 1.8. Well, there are no decimals in the 15. So therefore, my answer must be to a whole number. So I'm looking at the 6. I look to the right. It's greater than 5. So I'm going to round up, and my answer would be 17. Because the least accurate value has no decimal places. Let's now take a look at multiplication and division. Okay, so the rules for multiplication and division are as follows. 1, you do the math, and 2, your answer must be displayed to the least number of significant figures as presented in the problem. So in the first problem, 2.5 has two significant figures, and 3.42 has three significant figures. That means our answer can only have two significant figures. So that means to the 5, I am going to look to the right. That's 5 or greater, so I'm going to round up. So my answer would be 8.6. And the next one, 2.3 divided by 5.4, they both have two significant figures. So I don't have to decide here. Just means my answer can only have two significant figures. So that's to the 2. I look to the right, it's 5. I have to round up, so it's going to be 0.43 for my final answer. And in the last one, I picked values in scientific notation for a reason, because when you are given values in scientific notation, you may have to present your answer in terms of scientific notation, depending on what you're given. If it's a multiple choice problem, it might have it in decimal format, it might have it in scientific notation. So 1.75 times 10 to the third divided by 1.2 times 10 to the second gives me 14.58. Well, first of all, the top value has three significant figures, because we're looking at what's before the times 10 to the, and 1.2 times 10 to the second, that has two sig figs. That means our answer can only have two sig figs. So that's to the 4. And I look to the right. So there's two ways I can present this. I can present this as 15, or if I want to keep it in scientific notation, I can do 1.5 times 10 to the 1. Either one of those would be correct. So next we're going to talk about the heat formula. The heat formula is used to determine the amount of heat that is absorbed by or released by a substance or a compound. The heat is usually measured in calories. M, your mass, is in grams, so mass is usually in grams. Your specific heat, SH, that value is usually in calories per gram dot Celsius or Kelvin, depending on what they give you. And your change in temperature, which is delta T, change in temperature, triangle means change, is equal to T2 minus T1, and that's usually in Celsius or Kelvin, depending on the problem. So let's look at this problem. The specific heat of ethanol, so they gave us that, so that's my SH. Find the heat energy, so they're asking me to find heat required to raise the temperature of 193 grams. There's my mass of ethanol from 19 to 35. So there is my change in temp. So heat is going to equal my mass, 193. I'm not going to put the units in there. I'm going to put them down here just because it makes it easier to read, but I want you to see what happens to the units. This is grams, and that's times specific heat, which we said is 2.46. This one's in joules, but it would be calories. So I'm just going to, this went joules, so I'm going to put joules. Most of the time we're working in calories. Oops, I just said I wasn't going to put the units there. Let me put them down below. So that's times joules per gram dot Celsius. There we go. And our change in temperature is from 35 to 19. So that's going to be 16 degrees. 35 minus 19 is 16. gives us 7596.48. And I forgot to write Celsius down here. So notice grams cancels with grams, Celsius cancels with Celsius, and I'm left with units of joules or calories, which was what we were finding, heat. So that makes complete sense. Now that's a pretty straightforward problem because you are solving for heat, and that formula is set up to solve for heat. But sometimes you have to solve for something other than heat. So we're going to look at that in the next problem. So in this next problem, it says when a 120 gram sample of aluminum absorbs 9612 joules of heat energy, its temperature increases from 25 to 115. Find the specific heat of aluminum and include the correct unit. So you're solving for this specific heat. So before we can do the problem, you should set up the formula. So you have to get specific heat by itself. Well, this is pretty easy because all of these on the right-hand side of the equal sign are multiplied, and the opposite of multiplication is division. So we're going to divide both sides by m delta T, which is our change in temperature. And when we do that, this cancels and this cancels, and we have specific heat by itself. So let's rewrite the formula. And we have specific heat equals heat divided by m, and delta T is T2 minus T1. So that's going to equal, they told us the heat was 9612 joules. Our mass is 120 grams. And our change in heat went from 115 to 25, which is 90 degrees Celsius. So notice none of my units cancel, which makes sense because it's specific heat. So those units are either joules or calories. We happen to be working in joules right now per gram dot Celsius. So then all we have to do is the math, which comes out to be 0.89. And that is our answer. So just remember, if you have to solve for something other than specific heat, you need to isolate the variable and do the reverse order of operations. So we're going to review the density formula, which is fairly easy, but sometimes can be troublesome when you're solving for something other than density. So the best way to use this formula is if you have density equals mass divided by volume. When you write the formula out, if you remember to put a 1 under the D, then no matter what you're solving for, D, M, or V, you can just cross multiply and divide. So it says, what is the density of a piece of wood that has a mass of 25 grams and a volume of 29.4 centimeters cubed? So this one's pretty straightforward. My density is just going to equal 25.0 grams divided by 29.4 centimeters cubed. So that tells me that my density is going to be in grams per centimeter cubed. And I get 0.847 grams per centimeter cubed. If I wanted to put this in sig figs, both values have 3 significant figures, so I would leave it as 0.847. And there was actually a 4 that trailed after the 7, but you don't need that. So there's my final answer. In the next problem, it says, I threw a plastic ball in the pool for my dog to fetch. The mass of the ball was 125 grams. What must the volume be in order to have, I believe that says, let me just check, density. Yep, of 0.5 grams per liter. So here we know the density. The density is equal to 0.5 grams per milliliter. And we know that the mass is 125 grams. And we don't know what the volume is. That's what we're trying to find. So remember what I said, put a 1 under the density, and then you can cross multiply and divide. So you get 0.5x equals 125, and then you divide both sides by 0.5. And then you'll get your x. So the volume is 250, and this would be milliliters. And actually, I didn't write the density as exact as I should have. It was actually 0.500, which has 3 sig figs. So our answer has to have 3 sig figs. So there really should be a decimal there in order to make that 0 count. In the last problem, a piece of wood that measures 3 centimeters by 6 centimeters by 4 centimeters has a mass of 80 grams. What is the density? And would the wood float in water? Volume is equal to length times width times height. So we have to do a couple of things here. First of all, we are solving for the density. So we are using the density formula, but not right away. Density equals mass divided by volume. And we have to find the volume, which equals length times width times height. So that's going to be 3.0 times 6.0 times 4.0. So we've got 18 times 4. And that's going to be 72. And the units on that are centimeters cubed. So there's our volume. And they gave us a mass of 80 grams. So then 80 divided by 72 is 1.11 repeating. And that was 80.0 here on the mass. So our answer has to have 3 sig figs. Actually, no. Our answer, we got 3 sig figs here. Let me get this straight. And then we multiplied these 3. So this has 2 sig figs. So our answer can only have 2 sig figs. So our answer is 1.1 grams per centimeter cubed. So that's our answer on the density. Would this float? Well, assuming we're at standard temperature and pressure, no, because it's heavier than the density of water, which is 1, so it would sink. Average atomic mass. Average atomic mass is the mass of all the naturally occurring isotopes of that element. So you've heard me say this before. When we look at the periodic table and we look at carbon, element number 6, it has a mass of 12.011. That represents the average of all the naturally occurring isotopes of carbon, which are carbon 12, carbon 13, and carbon 14. In this question, it says copper occurs naturally as copper 63 and copper 65. Which isotope is more abundant? Abundant refers to percent, meaning which one has the greater percentage in nature. Well, if you look up copper, its mass on the periodic table is 63.546. So this copper is closer to the actual average mass than this one. Copper 63 differs by less than half a gram, where copper 65 differs by almost a gram and a half. So the one that is more abundant will be the one that is closer to the average. So here they're saying since our average value is closer to 63 than 65, we know that copper 63 is the more abundant isotope. And that was directly related to one of the homework problems on the second chapter. And a lot of people were confused by that and got it incorrect. So I wanted to make sure that I went over it. Normally, when we're calculating average atomic mass, average mass is equal to mass times percent plus mass times percent for however many isotopes there are. I'm going to do dot, dot, dot. There could be 2, there could be 3, and then we're going to divide that by 100. Okay, I replaced that bottom problem with another one because it was much more difficult than what you need to be able to do for this course. So we're going to look at this one. Calculate the atomic mass of potassium if the abundant atomic masses of the isotopes making up its naturally occurring samples are given below. So you have isotope potassium-39 that has a relative abundance of 93.12 and an atomic mass of 0.964, and potassium-41 with a relative abundance of 6.88 and a relative atomic mass of 40.962. Now, before we even start the problem, I want you to notice how this one is 93%, which means that our average when we're all done should be closer to 39 than it is to 41. So let's see. We've got average mass is going to equal 93.12 times 38.964 plus 6.88 times 40.962. And again, if you take it out of percent, you can use this as 0.9312, and you can use this as 0.0688, and then at the end, you wouldn't have to divide by 100. So whatever way is easier for you. So I'm going to total this up. You should do the same. And I get an average mass of 39.10 AMUs. And we said that we should come out closer to 39 because that one had the greater relative abundance. Quickly going through some of the more recent stuff, recall that in the nucleus of the atom are the protons and the neutrons, and the electrons are found in the shells outside. Remember that the last shell is called the valence, and these are the electrons that are involved in bonding. They will either give up electrons or gain electrons in order to attain 8. Metals tend to lose electrons and form positive ions, and nonmetals tend to gain electrons and form negative ions. Most of the mass of the atom is in the nucleus, and that's because protons have a mass of 1, neutrons have a mass of 1, and electrons have a mass of 0. But the atom in general is made up of mostly empty space, because that's where the electrons occupy the shells. And the atomic number equals the number of protons, and the mass number equals the protons plus the neutrons. And all atoms are electrically neutral, so protons equal electrons. To find the neutrons, we take the mass number and we subtract the atomic number. And you can review your homework for that. I'm going to briefly review naming compounds. I just posted the answer keys to the practice sheets on these from the other day in class, so I think that we've done quite a bit on this, and you just have to know the general basics. But all binary compounds, meaning all compounds that are only made up of 2 elements, and abbreviate compounds, end in IDE. If it's ionic, you name the metal, then the nonmetal with the IDE ending. So for example, SrCl2 is going to be strontium. I'm just naming the metal. And I take chlorine and I change it to chloride. If it's covalent, then we have to use prefixes. So we have mono, di, tri, tetra, penta, etc. Remember that the first one, if it's 1, we never name it as mono. We just name the element, so this is carbon. If the second one is 1, then we use the mon. So this is monoxide, because we can't have 2 vowels. If I have SO3, then this would be sulfur trioxide. If I have more than 1 on the first one, so if I have let's see, Si2O4, this would be disilicon tetroxide. And lastly, if polyatomics are involved, we simply are going to name the polyatomic. So if it's a polyatomic like NH4Br, we're going to name the poly, which is ammonium, and then change the ending on the bromine to bromide. So this is ammonium bromide. If it's 2 polys, then we just name them. So if it's NH4 NO3, then this is just ammonium nitrate. And I am giving you the polyatomic ion table. Quick review of bonding. Ionic. This is a metal and a nonmetal. Electrons are transferred. This is really important. And they're transferred from the positive ion to the negative ion, which is usually from the metal to the nonmetal, but if it involves polyatomics, it would be the positive polyatomic to the negative. We need to make sure that we show brackets and charge if we're drawing this. So for example, SRO, strontium, has got 2 electrons, oxygen's got 6 valence electrons, strontium's going to transfer 2 to the oxygen gained 2, it gets the brackets and a -2, and the strontium gives up 2. Sometimes you have to figure out what the formula is. If I were to say lithium and sulfur, you have to look these up, and you see that lithium is +1 and sulfur is -2, which means that my formula is going to be Li2S, which means that I need 2 Li's and 1 S, because each Li wants to give up 1. And sulfur wants to gain 2. So we can put an Li on either side. Each one gives 1 to sulfur, meaning each lithium becomes a +1 and the sulfur becomes a -2. Let's look at covalent. Remember that covalent is also another synonym for molecular. We're talking about nonmetals. Nonmetals. And there is a sharing of electrons. Sharing is caring, and covalent begins with C. Make sure that you count your number of electrons. If I have CHCl3, okay? Normally C goes in the middle. Why? Because it wants to form 4 bonds. It's got 4 valence electrons. So 4 valence plus 1 valence plus 3 times 7, because each chlorine's got 7. So that's 21, 22, and 4. I need to have 26 electrons when I'm all done. So I'm going to draw C, 1, 2, 3, 4. And then H can come in on one side. And then on the other 3 sides are going to be my Cl's with their 7 electrons. So when I'm all done, I count my electrons, and I can see that I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All 26 electrons are accounted for, and where they're actually being shared is where I'm highlighting in green. That's where they're connected to the C. There are 2 that you do have to know. So while we're here, this is covalent, but this is also a polar molecule. Why is it polar? Because it is asymmetrical. And there is unequal sharing. How do I know that there's unequal sharing? Well, 2 ways. Chlorine's got a higher electronegativity than carbon, right? So I've got this Cl pulling out this way, this one pulling this way. They cancel, but the Cl pulling downward is going to be greater than the H. So this is going to assume the slightly negative side, this the slightly positive side. So I have a dipole moment in the downward direction. And the other thing that you need to know is water. You need to know that water is polar. So we have H2O. Again, it's going to have 2 times 1 plus 6 is a total of 8 electrons. I draw my oxygen, 1, 2, 3, 4, 5, 6. And then H comes in here, and H comes in here. Oxygen has a higher electronegativity than H. You will have the electronegativity chart. This is going to be slightly negative, slightly positive. So my dipole moment is in the oxygen direction. Again, asymmetrical, unequal sharing. One that usually throws students that's really simple, but fairly easy, is just something so similar as HCl. Well, this is just 1 plus 7, and you've got H, and then you've got the Cl with its 7. Okay, but this is unequal sharing because chlorine has a higher electronegativity. So my dipole moment's going to be in this direction. All right. Now, still under covalent is nonpolar. So we're moving on to nonpolar. Nonpolar, I have no pull, and it is going to be symmetrical in shape. And there's going to be equal sharing. So this includes our 7-Up. So our Br, our I, 2, N2, Cl2, H2, O2, F2. All those molecules, the 7-up molecules. Because if one bonds to the other, first of all, it's equal, sharing, plus the electronegativity difference between the two is going to be equal to 0. And we talked about this at the last class. Another way to be nonpolar, is by symmetry. And I said that one that you should really be familiar with is CO2. And that's drawn like this with the double bond on either side. And you've got oxygen pulling out this way and pulling out this way. And you've got a double bond on either side. Remember, a double bond represents 2 pair or 4 electrons. A single bond is 1 pair or 2 electrons, and a triple bond is 3 pair or 6 electrons. Okay, I think that's all I have without making this too long. If there's anything specific that you have, I am staying for office hours Monday night, so you can ask me then. All right, have a great weekend.